All right, recording starting again. We're gonna switch over to clubs. Now, clubs, you guys were keeping these containers closed, but you were changing out the radial size, right? And so, I wonder what this is gonna look like. We're gonna have two graphs to do that. We're gonna start with V versus R, and then we'll do another manipulation. See how this works out. So let's start with the speed as a function of the radial size. Right, so here, go back to my visual. Right? I'm looking at what's the relationship between these two variables controlling for these two canisters. Okay. Right, so Kelly, you got some good data? Huh? Yeah, maybe. Well, we're gonna find out. What was your path to speed? Six hundred and something. So I'm gonna scale this. Let's go 200, 400, 600, 800. I think you should take care of that. 200, 400, 600, 800. Okay. And what was your largest radial size? 100. 100 centimeters? All right. Good. 4, 6, 0, 200. Whoops, wait a minute. Sorry, 20. Sorry, 20, 40, 60, 80, 100. That'd be radius in centimeters. There we go. All right, so data point time. What's one data point?
10 centimeters is
247 or something. Right up there. All right. Excellent.
At 30 centimeters, it was 402.5.
402.7. Bam. Right there.
At 40 centimeters, it was 478.
478. Bam.
60 centimeters,
483. Oops, not quite 500. Bam.
At 80, 612.
612.6. All right, so 5 data points. All right. Man, I think this is a class full of winners right here. I think you're going to be 3 for 3. Yeah. Yeah. Before I started recording anything, told you guys this is one of those labs that sometimes the graphs work out really nice and sometimes they're messy all over the place. I think all your guys' graphs are looking like what they should. So, which category is that going to be? Does that also look like this? You guys think? Right, look pretty close to. All right. Yeah, I'm thinking it's looking like some kind of root relationship. So I'm going to suspect that b is proportional to the root r. And if that's true, then b squared would be proportional to r. Okay. So we're going to see how close this lines up. V squared versus r. Okay. So you keep this radial scale the same. That'll just fit on the paper. So the radius in centimeters go 0, 20, 40, 60, 80, 100. Right. I need to square all these speeds. So speed squared, centimeters per second squared. Okay. So scale. See, 8 squared is 16. Zip, 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 zip. Okay, 160,000. This is 80,000. 40,000. 120. Something like that. All right. What's one data point?
At 10, it was 61,000.
Bam. The board. Right. Next one.
At 30, it was 165,000.
Wait, 30 centimeters was 160? Wait, what? What was oh. Hold on. I messed that up. I messed up my scale. I did. Oops. Let me go back and fix these numbers. Guys, H squared 64, right? 64, and then 0, 0, 0, 0. So it's been 640,000, which makes us 320,000. Right, which makes this like 160,000. Just like 480,000. Oops. All right, gotta go back and redo that one. Can you give me that very first point again? 61,000. So that'd be like probably right about there. Bam. Okay. All right, here we go. Okay, what's that? Next point.
At 30, it's 61,000.
Okay, it's right about there. Bam.
At 30, it's
200,000. So that'd be probably right about there. Bam.
at 60, it's 230,000.
It's right about there. Bam. Okay. And then
At 80, it's 374,000.
374,000. Right. Bam. Right about there. Ah, look at that. Look at that. Pretty dang close. That's about as good as it gets right there. So the speed squared would be proportional to the radial size. Okay. You make an equation with that. A linear equation like y equals mx plus b. About like that. Okay. So let's put this all together. These three stories. Got three stories we're putting together. Okay. This speed squared is directly proportional to the radial size. So if you like triple the radial size, it's not the speed that gets squared, but the square of the speed gets tripled. Right, right, right. The speed squared was also proportional to the hanging weight. And from this one, the speed squared was proportional to the reciprocal of the mass. So all together, it's going to go like, what's this thing? Speed squared was proportional to 1 over the mass. Speed squared was proportional to the hanging weight or the tension force. Speed squared was proportional to the radial size. Okay? So in one giant proportionality, you can say speed squared is proportional to, or directly proportional to. Okay? Well, we got the hanging weight, we got the radial size, and then divide by the mass. Okay? Just like that. Okay? Now, this force represents a few different things, right? Sure, it was the hanging weight, right? But think about it. That hanging weight was also equivalent to the tension in the string. Okay? And that tension in the string was acting as the centripetal force. So I'm going to put a little subscript C on this force because that force represents centripetal force. Right? So centripetal force, that center-seeking force, right? I could say is proportional to, okay, can you just take the m, cross multiply it and get mv squared, and then take this r and divide it down over r. So going from here to here is just an algebra shuffle away. Right? Now, one last thing. I could say proportional, but I can actually do one better. If you go back and look at any one of your data points and like, run a calculation for it, actually it ends up being equal to. Right? Like if it said proportional, I'd say, well, there might be like some constant out here. Like, is it a factor of like 1/2 or something? No, it ends up being like 1 exactly. So I can say equals. I can say equals. Okay? So this is here. There's one of your places right here. Okay? So it's called centripetal force. In this case, provided by weight, the tension, centripetal force. Right? Take this mass, multiply by speed squared, divide by this radial size. Right? That's what's going to hold these in balance right there. Okay? So. What's that? Yeah, hold it like an equilibrium, right? Like so that this hanging weight could be in equilibrium, right? Yeah, that's what I look for. Centripetal force is mv squared over r, right? There's all sort of things you can do with that. You guys remember Newton's second law of motion? Acceleration is force divided by mass, right? So centripetal acceleration is involved with like, if you just divide by the swinging mass, right? You guys remember like way back in the day, I said inside a car, you can't feel the speed of the car. You can feel like a change in motion. You can feel speed slowing down. That's acceleration, right? And also like the steering wheel. So if you're going around a curve, you can feel that too. And I said, don't worry about that one. We'll just focus on back and forth for now. It says someday we'll focus on like turning in a circle. hey, look at heresies, right? So if you're like going around a curve in a car, the faster you're going, like the more you feel that, like you feel some kind of G's, right? Right? The faster you're going. And also the tighter the curve. So the smaller the radial size, the more you have to accelerate going around a curve too. That's why if you have a big wide curve, it's a more subtle effect, right? Versus if it's a tight curve, ooh, you can really feel that. Ooh, right? Right? Something like that. Going curve, right? Okay. Right. So you guys good there? All right. Got just a few minutes of class left. Um, yeah, that's okay. Okay. Last 2 minutes of class. I'll go ahead and just show you guys some posters we haven't quite done yet. How about that? Okay. And then here, just turn in your lab data, your tables and graphs to the grade tray before you leave class today. Okay. But see for the rest of class here, here's O'Neill cylinder review. You have like a rigid like a turntable or some kind of cylinder. Suppose you're out in space, right? And this was one of the videos I showed you guys too. Remember that giant space wheel that was rotating? Right? That was one of the questions that was floating around as well. How fast would this have to rotate so that if you're walking around on the inside, you feel like there's no gravity? Okay? Well, we can put together different parts of physics to start to answer that now. Like you guys know, centripetal force is mv squared over r, right? But the weird thing about like the O'Neill cylinder is that suppose you like walk up this ladder. You guys see this ladder is like the diameter of the cylinder. You get all different linear speeds, but everybody has the same angular speed. Kind of reminds me of the coils type, right? Where everyone on Earth has the same angular speed. Okay? So there's maybe a better way to represent centripetal force for like this rigid rotating disk, right? Which is you can substitute for this V. You guys can substitute omega times r. You guys remember that turntable, right? Omega times r, and one of the r's cancel, and you get something that looks like this or this, right? Oh, now you have a way to figure out how fast you have to spin this in like radians per second. So you can target 9.8 meters per second squared, like for some radial size, so that all these people feel like they're in Earth gravity, like walking around on the edge, even though they're just rotating around, right? And if you take suppose it's spinning and the walls like fall away, you're just gonna fly off in a straight line, right? But put the walls there, they can't fly off in a straight line according to Newton's first law of motion because the wall is holding them in. That's like centripetal force. In this case, it's like it's a normal force. Right? Also, we got a conical pendulum, right? Technically, you guys had conical pendulums, but the pendulum was so flat, we treated it as a flat circle. It would have been like close enough, right? Right. Ooh, so we could figure out like what's the relationship, like this angle, the speed is going around, this radial size here, okay. The tension of the string, okay. Some kind of relationship. Okay. Oh, hey, a car turns on a big track. That was the example I just gave you, right? Suppose you're exiting I-95 or getting on 95 for that, right? Some kind of curved track, right? You have to make a curve, right? Do you guys think if you were a road engineer, suppose you thought this might be an icy road, and so you wanted cars to be able to make the turn without any friction? I'm showing no friction here, right? So maybe there's like some ideal speed, like some speed limit, like okay, I know it's going to be about 40 meters per second or miles per hour or something, right? Oh, I know the radius of curvature is going to be such and such. I know what Earth gravity is. What angle do I have to bank the road to let this car make the curve with no friction, right? So you could find that. Wait, why do I have two of these? Oh, this is an old one. Okay, here's a new one. Has the answer on it. Okay. Oops. Okay. Oh, and then there's universal gravitation, which we haven't quite got to yet, but we're going to combine that with centripetal force and make orbits is what we're going to do. All right, so that'll be next week's adventure and bringing gravitation and continuing that story from there.